Lecture Monday. The special lecture will not be on material and art, but on more advanced material, in particular some research I did on this subject, which I thought maybe would give you an idea of what's going on today in the subject. And then we'll have review and all kinds of lectures, etc., to get ready for the exam and reading period, and that will be posted on the web. So we won't arrange it on the now. Good. So where were we last time? Last time we determined what all the algebraic integers in the field q square root of d, where d was a square-free integer. And the algebraic integers formed a ring, which we'll call R. And in the case, there were two possible cases. Well, there was the case where you always contained all integers plus integer multiples of square root of d. And that was all you got when d was congruent to 2 or 3 mod 4. And in the case where the d was congruent to 1 mod 4, you got a little more. So you certainly got the integers, you got the multiples of square root of d, but you also got the multiples of 1 plus the square root of d over 2 when d was congruent to 1 mod 4. So in particular, the algebraic integers form a ring. And that ring is the ring we're going to study from now on. Now, there's a uniform way of writing this, a nice uniform way of writing this. So in other words, the things in the algebraic integers are of the form a plus b root d, where a and b are integers, or a and b are half integers, which are not integers. They both have to be either integers or half integers, and this occurs when d is congruent to 1 mod 4. Because the multiples of this number have a and b both half integers, neither integers. Right? If you multiply by 2, then a and b are integers. But if you multiply by 3, a and b are half integers. So these are the set of algebraic integers. Now, the uniform way of writing this is to introduce a new number, which is a better number for describing this ring of integers, capital D, which is either 4d or d. This is the case when d is congruent to 1 mod 4. And this is the case when d is congruent to 2 or 3 mod 4. In which case, this number here becomes congruent to 0 mod 4. So this capital D is either divisible by 4 or has remainder 1 mod 4. And then if you introduce that, there's a uniform way of writing down this ring of algebraic integers. You can write it like this. This is a cute way of doing it. It's all multiples of 1 and all multiples of d plus root d over 2. Now, why is that? Because first of all, the square root of d is either equal to 2 times the square root of little d or the square root of little d, depending on what happens. So in the case where d is congruent to 1 mod 4, this is little d plus the square root of d over 2. But little d is odd. So if you can subtract an integer from it and get this number. And conversely, if you had this number, you could add an integer to it and get that number. So this ring is the same as this ring when capital D is odd. If capital D is divisible by 4, so square root of d is 2 little d, then both this number and this number are divisible by 2. You can divide the 2 out, and you're left with an integer plus a multiple of square root of d. So you can express square root of d, and vice versa. So this is the uniform way of describing the ring of algebraic integers. And we could call this R sub D or something like that. That's why I say it's easier to index by this capital D than it is by the little d. So for example, now we're going to study these in particular when D is negative. They're called imaginary quadratic rings. And we're going to see right away at the beginning of this lecture why this is an easier case than the positive. And if you list out the possibilities for D that are less than 0, as I did last time, they look like -3, -4, -7, -8, -11, -12 is no good, -15, -16 is -19, -20, -23, etc. So there are an awful lot of interesting rings indexed by this. And this case here, this D is equal to -4, is where D is equal to -1, and that's the Gaussian integers. So that's the case we've looked at. And all these other cases are new rings that are going to be interesting for us to study. So does everyone see how just taking an integer, defining a ring like this, you get an interesting ring which may or may not have unique factorization, which we're going to want to study. Okay. Now the first thing to show you why this case is easier than the positive case, which are called real quadratic rings, let's just observe that we have the following map. I claim we have a map, delta, which Artin calls the norm map. That's the usual notation from it. From the ring R to the ring Z. In any of these cases. And the map looks like this. It takes something of the form a plus b root d. And if I want to take the norm of it, I take it to a squared minus d times b squared. In other words, that's the product of this number, a plus b square root of d, with the other number, a minus b square root of d. If this thing is called alpha, then this number in the ring is called alpha prime. There's a way of taking the ring to itself, which takes this number to its, in some sense, its conjugate. And if you multiply these two numbers in the ring, notice that the terms before square root of d go away, because you have ab square root of d with a minus sign, but here you have ab square root of d with a plus sign. So you just get a normal number. Now I claim that number is an integer. That's not completely obvious. It's completely obvious in this case, when a and b are both integers. But you have to check that it's an integer when a and b are both half integers. But if a and b are both half integers, then the fact that d is 1 mod 4 means that this number turns out to be an integer. I mean, it's a priori it's 1/4 of an integer, but you'll check, you see that a squared is congruent to 1 mod 4, and b squared is congruent. So you'll see that this number turns out to be an integer. So in particular, this product of the number a plus b root d times this other number is an actual integer. And this map, which takes elements of our quadratic ring to elements in the normal ring, has the nice property that if you take the norm of a product, it's the product of the norms. We saw this in the Gaussian numbers. And the reason is that this norm of a product is just alpha times alpha prime times beta prime. Well, really, it's alpha beta times alpha beta prime. And you find that alpha beta prime is alpha prime times beta prime, and then you rearrange it. And then you rewrite it as alpha alpha prime times beta beta prime, using the fact that multiplication is commutative in this ring. And then you recognize this is the norm of alpha and this is the norm of beta. So it's multiplicative. It's not additive, but at least it's multiplicative. Okay, so this will allow us to identify, as we did in the Gaussian numbers, what the units of the ring are. One more observation. And this is the reason that this, or d less than 0, this is the reason that this condition becomes so nice. If you look at the norms, this is an integer, but when we're in the imaginary quadratic case, it's a non-negative integer. because this is a square, and we have a minus d here, so we're taking the sum of positive numbers. So this is really what makes imaginary quadratic case so much easier. The norm is non-negative. Now I claim we have the following result on units. And this is true in all cases. Proposition. Alpha is a unit in R. In the ring R, if and only if the norm of alpha, which is plus or minus 1, is a unit in Z. Okay? So that you can test whether this thing is invertible in the ring by calculating this integer and seeing whether it's invertible in the integers. Proof. If alpha is a unit, there exists a beta in the ring where alpha times beta is equal to 1. That's what a unit means. Apply the norm. Then the norm of alpha beta, which is the norm of alpha times the norm of beta, is the norm of 1. But the norm of 1 is just 1, because b is equal to 0 and a is equal to 1. So here are two integers whose product is 1. Therefore, the norm of alpha has to be a unit in the integers, and consequently, the only units in the integers are plus or minus 1. Conversely, if the norm of alpha, which remember is alpha times alpha prime, is equal to plus or minus 1, then plus or minus alpha prime is an inverse for alpha. And this element is in the ring too, because if a plus the square root of b, b square root of d is in the ring, then a and b are both integers or half integers. Consequently, these are both integers or half integers, so this is in the ring. And there, that gives you the inverse, because here's a thing that you multiply it by. You either get plus 1, in which case alpha prime is an inverse, or you get minus 1, in which case minus alpha prime is an inverse. Okay. Thus, corollary, if d is less than 0, then alpha is a unit if and only if the norm of alpha is plus 1. Because in that case, we saw the norms are all non-negative, so you can't be minus 1. All right, now let's enumerate the units in the negative case. In fact, if d is equal to minus 3, there are 6 units. If d is equal to minus 4, there are 4 units. And if d is less than minus 4, there are 2 units. In fact, in this case, the unit group is the same as the unit group of z, just plus or minus 1. So for almost all these cases, except for the first 2, you don't get any new units in the ring that you didn't know about. Nothing is invertible except when a is equal to plus or minus 1 and b is equal to 0. All right, let's prove it. Well, we're looking for solutions. Proof. A unit, alpha is equal to a plus b squared to d, is a solution to a squared minus b squared d is equal to 1, where a and b are either integers or they're half integers. Okay, now look at this. Okay, if b is equal to 0, right, then a squared has to be plus or minus 1. So, a squared has to be 1. Sorry, so a is plus or minus 1, and there you get the units in z star. Those things we already knew about. if b is bigger than 0, then, or b is not equal to 0, I'm sorry, then minus b squared d is bigger than or equal to d over 4, right? Because b, whatever it is, b is in absolute value bigger than a half. So b squared is bigger than, so it's minus d over 4. How about that? Because, I mean, this has got to be b has got to be a half integer. So this has got to be minus d over 4. Once minus d is bigger than, if minus d is bigger than 4, it's hopeless. Right? Because then this number will be bigger than 1, and there's no way that these things can add up to 1. This number is positive. Right? So that eliminates almost everything, and then you just check these two cases, and you find the various solutions. They're a finite number. On the other hand, look at what happens if d is positive. If d is positive, this is the difference of a square and some multiple of a square. Right? So that you could certainly imagine that difference being 1, no matter how big a and b are. I mean, they're not adding up. You're taking a square times, an a times square minus d. And in fact, it turns out that if d is positive, there are always an infinite number of units. Fact, which I'm not going to prove. If d is bigger than 0, r star is infinite. And that gives a lot of headache. I'll give you an example. This first simple example. Example. D is equal to 5. That's the smallest positive d. So there r is equal to z plus z times 1 plus the square root of 5 over 2. Now let alpha be the number 1 plus the square root of 5 over 2. This is a famous number in the history of math called the golden mean. Okay? It's if you build a rectangle such that when you chop off a square you get a similar rectangle, then the ratio of the sides is that. The Parthenon, for those returning to Greece for the holidays, has dimensions the golden mean. All classical architecture was built on the golden mean. Corbusier, one of the great 20th century architects who designed the Carpenter Center, where many of you may have taken drawing classes, believed that architects should not be given rulers. They should just be given a stick in which it was marked out 1 and the length of the golden mean. Everything should be designed according to that. Anyhow, here's this alpha is 1 plus square root of 5 over 2. Now, if you multiply alpha times alpha prime, you get 1 plus the square root of 5 over 2 times 1 minus the square root of 5 over 2, which is 1 squared minus 5 over 4, which is minus 1. So that shows by our proposition up here that alpha is a unit with inverse minus alpha prime. Okay? So here's one unit. To find an infinite number of units, you calculate alpha squared. So alpha squared turns out to be 3 plus the square root of 5 over 2. Okay? If you multiply, you get 1 plus square root of 5. That's 6 plus 2 square root of 5 over 4. And then you divide out, you get this. So this is also a unit because delta is multiplicative. So we find that the norm of alpha is minus 1 implies the norm of alpha squared is plus 1. So that's another unit. Okay? Then you take alpha cubed. You get another unit. Let's see what it is. 9 plus 5, that's 14. So it's 7 plus 3 square root of 5 over 2. That's another unit. That one has norm minus 1. And you keep taking powers of alpha, you never get back to 1. In fact, the a's and b's keep getting bigger and bigger. So this is a unit because 7 squared 49 minus 9 times 5, 45, is equal to 4. Or maybe minus 4. What did I do wrong there? Yeah. How can this norm be minus 1? Yeah, I mean this... Yeah, the norm of alpha cubed is minus 1, but I mean it's the fact that you have an approximate solution to this is equal to 1. In fact, this turns out to be 4. Okay? Okay, so here you get an infinite number of units. Alpha to the n are all distinct. And in fact, the fact that this group is infinite is related to a famous classical result in mathematics called the solution of Pell's equation, which Euler worked out using the theory of continued fractions. We're not going to go there. That's a really interesting subject. You can read about it more in Artin. But here, we're just going to concentrate on these fields with negative discriminant where the unit group is finite. In fact, the unit group is almost always just the unit group of the integers. And we're going to go on to study a little bit more of the ideal theory. Okay? Now you might say, well, this is getting awfully specialized. Why are we doing the ideal theory of this silly ring? And the reason is, this is where ideals were discovered. And it's all very nice to have an abstract theory of rings and an abstract theory of ideals and principal ideals, etc. But this is the place where people first came to grapple with the fact that there were non-principal ideals and figured out what to do about it. So it's often nice to look at the original problem from which the entire theory arose. All right, now, we saw that when D was equal to, when D was equal to minus 1, so we got the Gaussian integers, is a Euclidean ring. However, I claim that if D is 3 mod 4 and D is less than minus 1, namely for all the other cases which are negative, where D is congruent to 3 mod 4, I claim then R, which is Z plus Z root D, is not a unique factorization domain. For example, we saw this for D is equal to minus 5. But it's also true, so if you add, it's also true for minus 13. And it's also true for minus 17. And it's also true for minus 21, etc. So all that infinite number of D's, we're going to get a non-unique. So this is a completely atypical result. And remember, we used the fact that a squared plus b squared was somehow, if a and b were both less than a half, a squared plus b squared was less than 1. But here we're going to have things like a squared plus db squared. And that's not going to be, or minus db squared, and that's not going to be less than 1. So to show you this, I have to give you a factorization of something in 2 different ways and show you that the factors are prime elements. All right, so consider the factorization of 1 minus d. So I'm going to write 1 minus d in 2 different ways. I'm going to write it 1 plus the square root of d times 1 minus the square root of d. And I'm going to write it as 2 times 1 minus d over 2. Now, since d is 3 mod 4, it's an odd number. So if I subtract it from 1, I get an even number. So this is an integer. This is an integer. Those are elements in our ring. And these are certainly elements in our ring. Okay? So I claim 2 is an irreducible, or is a prime, an irreducible element, a prime, in R. 2, the number 2. So you can't factor 2 in any essential way in this ring. Now that was false in this ring. In this Euclidean ring, you could factor 2. 2 is equal to 1 plus I times 1 minus I, and neither of these were units. But in these rings, I can't factor 2. Proof. Why? Suppose 2 was equal to alpha times beta, with neither alpha nor beta a unit. Then take the norm. The norm of 2, which is equal to 4, is equal to the norm of alpha times the norm of beta, because the norm is multiplicative. So a lot of our study of this ring is going to be using the norm to turn it into a property of the integers. Now, if alpha and beta are not units, what do we know about their norms? Not equal to plus or minus 1, or in this case not equal to plus 1, because the norm is positive. So here we have 4 written as the product of two integers, neither of which is 1. What does that tell us about the norm of alpha and beta? There have to be 2. Therefore, we have found in this ring, if we had a factorization of alpha and beta, we found elements of norm 2. Now that's okay in this ring. These elements do have norm 2. Here's the element alpha, here's the element beta. Both of them have norm 2. All right? But here, this is impossible. We write alpha as a plus b root d, where in this case we know a and b are integers, right? Because we're in a case where d is 3 mod 4, so the ring of integers is just this. Yeah, Tim. Pardon? No, because remember, in an imaginary quadratic ring, the norm of alpha is always greater than or equal to 0. It's a squared minus db squared. A squared and b squared are positive, and d is negative. So this number is greater than or equal to 0. Okay? So in general, when we were doing units in general, we had the possibility of minus 1 for real quadratic. But in the imaginary quadratic, the norm is always positive. So that's why they don't have to be plus or minus 2. They really have to be 2 here. Okay, now this is impossible because if we write alpha like this, the norm of alpha is a squared minus db squared. Now, if this is equal, how could this possibly be equal to 2? I mean, this number is quite large. Once d is, so d is at least, minus d is at least 5. So this number would be at least 5 times b squared, or 13 times b squared. So there's no way that could be equal to 2. So this would imply b is equal to 0, as minus d is greater than or equal to 5 on our list. And since b is 0, that would imply a squared is equal to 2, which is a contradiction because 2 isn't a square. Now you see, again, this would be very, very difficult to check in the real quadratic case. I mean, it's certainly possible you could have a very big A and a very big B such that this thing could equal 2. This could be huge, this could be equal to huge, and their difference could be 2. But they can't add up to 2 if they're both positive. Okay, so therefore, we get a contradiction. So therefore, 2 could not factor this way. So therefore, 2 is an irreducible element. Now, here's why we can't have a unique factorization domain. 2 divides 1 minus d, because here's a factorization of it. Therefore, if 2 were a prime element and we had unique factorization, 2 would have to divide one of these two things, right? And if you have a unique factorization domain, you have a prime that divides a times b. It divides a or b. That's by this Euclidean algorithm argument. But 2 doesn't divide either this or that. Because if we tried to divide 2 into this, we'd get 1 plus square root of d over 2, which is not an algebraic integer. Right? We know the algebraic integers in this type are just integers plus integers. And likewise, 2 doesn't divide this because its quotient is not an algebraic integer. So therefore, we have a prime element, we have a factorization, it divides neither part. Therefore, we can't have a unique factorization domain. Yeah.
Could you just say the last part again about if 2 divided 1 plus
If 2 divided 1 plus d, we'd have the following factorization, Atticus. We'd have this. 2 times 1 plus the square root of d over 2. That's the only way you can write it. Right? But this number is not in R. Because it's not an algebraic integer. A factorization has to take place inside the ring. This is the only way it could be written inside the field.
Why is it not an algebraic integer?
Why is it not an algebraic integer? Because if you take its delta, it's not an integer, for example. It doesn't satisfy a polynomial with integer coefficients. Monic polynomial. That's what we worked out last time. That the set of algebraic integers when d was 3 mod 4 was just this. Integers plus integers times square root of d. This is a half plus a half square root of d. Okay? So that's not any good anymore. Now this argument only works for d congruent to 3 mod 4. And it turns out there are other cases besides the Gaussian numbers that are... It's a not unique factorization, so let's even stronger. Not every ideal I in R is principal. Because if every ideal were principal, we have unique factorization domains. Okay? Now, it is always the case for all of these rings that every ideal can be generated by 2 elements. Principal means it's all multiples of 1 element. But no matter what these rings are, any ideal can be generated by 2 elements. Although not all ideals I in R are principal. That means that I is all multiples of 1 element. Every I can be generated by 2 elements. That's not true in any ring, but it is true in these rings. So they're not the worst thing in the world, even though they're not always Euclidean or principal ideal domains. Why is that? Why? Well, the first claim is either I is equal to 0, in which case it's generated by 1 element, or I has finite index in the ring R. In other words, R mod I is a finite ring. Okay, proof. If alpha is not equal to 0 in I, then the norm of alpha, which is alpha times alpha prime, which is some number n bigger than 0, is also in I. So it's the same argument we made from the Gaussian integers. So the principal ideal, all multiples of n, is contained in I. Once I have an integer, I have all multiples of that integer, and that's contained in my ring R. And this index is finite and is equal to n squared. Because if R is z plus z times d plus root d over 2, then this multiples of n is just nz plus n times z times d plus root d over 2. And the different cosets are given by the different residues of A and B mod n. And there are n squared possibilities for them. N squared possibilities for A mod n and n squared possibilities for B mod n. So the index of this principal ideal in the ring is n squared. And I is squeezed between this and this. So the quotient of R mod I is finite and is of order less than n squared. The index of R mod I is less than or equal to n squared. Okay? Same argument we made for the Gaussian integers. So it's a finite index. Now, It's a fact. Now, Artin likes to draw pictures of these, and in fact, pictures are quite useful. So we're going to draw a picture of R, and we're going to draw a picture of I. We draw a picture of R inside of the complex numbers. And we draw it like this. The first thing we draw is the element 1. That's certainly an R. And then we draw the complex number, which is the other generator of R, namely this d plus root d over 2. Now that either... So I'll draw that. That's up here somewhere. I don't know. Let's put it up here. It's a d plus root d over 2. Root d is an imaginary number because... actually, that's not the way to draw it, but never mind. I mean, the real part is much bigger than the imaginary part, so it really looks more like this. But never mind. D plus root d over 2. Okay. Now, R consists of all integer multiples of this, so 2 and 3 and minus 1 and minus 2, etc. And all integer multiples of this. So you get this and this and this and this. And then you get all integer multiples of this plus all integer multiples of this. So you also get this and this and this and this and this. So these points in the complex plane form what's called a lattice. And R consists of exactly those points. So we've seen this for the Gaussian numbers, where you get the rectangular lattice. Another nice case is where d is equal to minus 3, and you get the hexagonal lattice. And in general, you get some subset of the complex plane which is stable under addition and multiplication, but a discrete set of points in the complex plane. Of C, stable under multiplication. Now, this ideal consists of a subgroup of this lattice which has finite index. Namely, it might not contain 1, it might not contain 2, but it contains some integer out here, n, we saw, because no matter what we have in it, its norm is then in the ideal. So it has some multiple of that. Right? And then it has some other collection of these lattice points, and that forms the ideal. So it also gives a discrete subgroup of C. I in R is a smaller subgroup. Not necessarily, and it is stable under multiplication, but even better, it's stable under multiplication from R. And in general, all you have to do is check that it's stable under multiplication by this one element in R, because it's a subgroup. So that means it's stable under multiplication by 1. I mean, obviously stable under multiplication by any integer, because if you multiply by 2, you're just adding a thing to itself. So it's stable. But then if you check that it's stable under multiplication by this element, and it's stable under multiplication by 1, then it's stable under multiplication by any sum of 1 and a multiple of this element, and then it's stable under multiplication by R, and that's what an ideal is. So pictorially, first you draw R, and then you might draw a subgroup of R, which is stable under multiplication. So I'll give an example. Let me draw an example of this so that we don't totally freak out, and then we'll do this two-element business. I'll draw a good example for you, if I can. So let's take the case where D is equal to minus 3. So that's the case where you get a very interesting lattice. So this is congruent to 1 mod 4, so it's the same as D. All right. So the original R can be written as Z plus Z times minus 3 plus the square root of minus 3 over 2. And that's the same group as Z plus Z times 1 plus the square root of minus 3 over 2, because this differs from this by just adding 2 to it. So you get the same group. All right, let's draw this lattice, and then we'll draw an ideal. And we're going to draw the principal ideal. So we're going to take the ideal I as the ideal generated by the square root of minus 3, all multiples of square root of minus 3. All right, so here we go. The first thing is we have to draw 1. Then we have to draw the other generator, which I'm going to do this. Now this is a complex number which has real part a half and imaginary part root 3 over 2. And it turns out to lie on the unit circle, as you know from your basic trigonometry, and it's up here. It's 1/6 of the way around the unit circle. That's the 1 plus the square root of minus 3 over 2. So it's a number of complex absolute value 1, because if you take its absolute value, you get 1 plus 3 over 4, which is 1. Its real part is a half, so it lies right there. This is a 30, 60, 90 right triangle. Okay? And now, let's draw all the other. So if I take this and I take this minus 1, I get this number. Then I also have minus 1. Then I have minus this number. Then I have minus that number. And those are the 6 points in this ring which have absolute value 1. Namely, those are the 6 units of the ring. Okay? Now, do we have anything which has absolute value 2? So these are the things that are absolute value 1. So then we can go to the... Now, we have certainly 2 in it, but this thing has norm 4. Right? The next question is, could we get anything on the circle where the radius of the circle is square root of 2? Do we have any solutions of norm alpha equal 2? Well, this would be a squared plus 3b squared, where a and b are half integers. Right? And the answer is you can't find such solutions where a and b are in 1/2 z minus z, or a and b are in z. So there are no elements on the circle of radius square root of 2. All right? How about norm alpha equal 3? Are there any things whose norm, can you solve this as equal to 3? How? A is equal to 0 and b is equal to 1, right? So that would be the element square root of 3, which is about 1.7, right? So we go up here. So that's when you add these two things, you get this thing, which is the element square root of minus 3. That's the next closest thing to the origin. Now, once I have this thing, I have all multiples of it by units, which don't change the norm. So once I find one thing of norm 3, I must have 6 things of norm 3. And I get them by multiplying by these things, which means by rotating around exactly 60 degrees. So here, if I rotate around 60 degrees, the next thing is here. Oh, this is beautiful. Peter knows why I like this so much. You guys don't know yet. But the next thing is here. The next thing is when you rotate around by 120 degrees, you should get something here, right? Then we should get the minus of this. Then you should get something out here. A little too far, but okay, right there. And then we should get something out here, which is the sum of this and this. And then you should get the element 2. So here are our 6 things in the lattice that have, except I didn't do them very well. This thing has the same height as this. So these things are all on a straight line, and these things are all on a straight line if you draw them correctly. There you have it, Peter, the root system of type G2. Right? Let's see why I like this so much. I used to be able to do this well. If you draw a Jewish star through the 6 outer points like that, then the edges are on the 6 inner points. Nice, huh? Just celebrating the holiday season. Okay, now, this is just the elements of norm 1 and 3 in the thing. However, I claim that these 6 elements here are all in this ideal. Right? Whereas these elements, these 6 elements in here, are not in that ideal because we've seen that these 6 elements are square root of minus 3 times units. And in fact, if you take this ideal, it can be generated by this element here and any of the others because they give a basis for the subgroup. And in general, and this is something I'm just going to ask you to accept to prove this theorem, is that any subgroup of R of finite index can be generated as a subgroup. Forget about the fact that it's an ideal by 2 elements. It's a fact about discrete subgroups of the complex numbers. They're either generated by 1 or 2 elements. In fact, didn't we prove that when we were doing subgroups of the group of motions? If you took the plane, right, and you had a discrete subgroup of translations, right, it was either 0 or generated by 1 element or generated by 2 elements. Thank God we did discrete groups of motions. Whatever this thing is, it's a subgroup. Forget about that it's stable under multiplication. It's a subgroup. It's discrete. The complex numbers, whatever else they are, forget about their multiplication, form the plane. So this discrete subgroup is generated by at most 2 elements. So here are the 2 generators of the subgroup. Forget that they are stable under multiplication. So that's why, since it's a subgroup, you can generate it by 2 things. So we can certainly generate it by this, for example, and this. Well, you can imagine having a computer print out on a big piece of paper all the elements of this lattice. This is a particularly beautiful lattice. If you circle spheres at radius 1/2 at the points in this lattice, I'm not doing it very well, but there they are. So you take the centers of the spheres to be the points of the lattice, and you take the radius of the spheres to be 1/2, so the spheres don't intersect. Then you get the best packing we know of spheres in the plane. In fact, it's known to be the best packing of spheres in the plane, called the hexagonal packing. The reason is around each sphere you have exactly 6 spheres. And this doesn't cover all the space of the plane. It covers close to 90% of the space of the plane. And this is the best sphere packing in dimension 2 and was discovered 1 billion years ago by the bees. Right? That's the way you pack honey in a hive if you want to make circular packings and you want to store as much honey as possible. So nature has an amazing way of solving extremal problems. And nature has solved this problem many, many times, many years before the mathematicians got to it. You'll be happy to hear that Professor Elkes, working with one of his distinguished graduate students who's now at Microsoft, has found the best packings of spheres in dimensions 8 and 24 recently. We knew that they were, but he's been able to prove it. Now, we don't have any bees that are working in dimension 24. However, it used to be, I just love this. It used to be the fact that when mathematicians would talk about some phenomenon in dimension 8 or dimension 12 or dimension 24, 24 happens to be an absolutely magical dimension for mathematicians. So they talk about this, and the people who are doing hard science would laugh, and they'd laugh, and they'd laugh, and they'd say, well, you can't tell us anything because in 2 dimensions we've known this for billions of years, and in 3 dimensions we've known it for millions of years, and you can't even do anything, and we don't care about more than 3 dimensions, right? Okay. Now, if you just go over to Jefferson, now, half the people are talking about what happens in dimension 10 and happens in dimension 11, because those are the only dimensions they can resolve the differential equations of physics. So now it's believed that we live in a 10-dimensional universe of which we see 4 dimensions. 3 of them are space, 1 of them is time, and there's 6 tiny little dimensions, all in a little manifold of dimension 6, about the same size as Planck's constant, so we'll never see it. But it has a very important shape called the Calabi-Yau manifold, named after Professor Yau here, and that shape resolves all the difficulties of differential equations in the universe. So I just love this, the fact that all at once, they're really into what happens in dimension 24. Can you tell us more about dimension 26? And each one of these dimensions has its own charm. But here's what happens in dimension 2. Okay? So we find that ideals are generated not necessarily by one element. We've shown that there are plenty of cases that aren't PIDs, but they're generated by 2 elements. Now, on Friday, Peter's going to show you how you rescue unique factorization in these rings, because that was a huge discovery in the middle of the 19th century by mathematicians. That it was discovered that you couldn't always factor an element into primes. We've gotten examples of that. But you could factor ideals into prime ideals. Namely, there was a generalization of multiplication that took place for ideals. Then there was a generalization of irreducible elements that took place for ideals called prime ideals. And that every ideal could be written uniquely as a product of prime ideals. That's a big, big, big result. And then Peter will also show you how you measure how far one of these rings is away from being unique factorization. And that's something I've worked on a lot, and I'll talk to you about that on Monday. Okay? See you then.